There are two other texture mapping methods that can add considerable detail to a model. The first is displacement mapping. Here a texture, called a height field, is used to change the height of the surface itself at each vertex. In other words, each vertex has a UV value. This value is used to retrieve the height value from the texture. The height value is then used to displace the vertex, in other words, move it upward or downward along its normal. However, simply displacing the vertices does not change the shading normals of the surrounding surface. You would see the bumpiness in the silhouette of the object, but otherwise the shading would look fairly similar to the original. To change the shading normals themselves, another texture is applied to the surface. This texture is called a normal map and is considerably different than other textures we've encountered up to this point. Here's the displacement map for the model, and here's what the normal map looks like. The gray level of this height field shows the amount to displace the vertex, with brighter pixels pushing farther above the original surface. The normal map is in fact derived from this displacement map, and there are tools to create this type of texture. Each normal in the normal map is found from the differences in the nearby heights in the displacement map. You can always tell a normal map by its distinctive light blue. The normal map stores an XYZ direction vector at each texel. When we view this XYZ value as an RGB color, we get this type of look. Specifically, the red channel is X with positive to the right, the green channel is Y with positive up, and blue is the Z-axis. This XYZ space is relative to the surface of the model and is called tangent space. If the normal is not to be changed at all, the normal stored is 0, 0, 1, straight up the Z-axis. A value of 127 in this texture means 0, a value of 255 means 1. The light blue then comes from an X and Y value of 0, which gives a red and green channel of 127. The Z value is 1, giving a blue channel of 255. So an unchanged normal has an RGB of 127, 127, 255, a light blue. The basic idea is that you're using this normal value to change the existing shading normal. The normal in the texture map takes the place of the shading normal, and relative to the shading normal's original direction. Here's the interesting part. Once you have the normal map, you don't have to apply the displacement map. They're separate processes. The displacement map moves the vertices, the normal map modifies the shading normals. Here we have, from left to right, the unmodified head, the head with just normal mapping, and the head with both. While the model with both mappings is the most convincing, using just the normal map gives you much of what you want but with many less triangles. In fact, artists often first create highly detailed geometric models. A program can then bake the normals into a normal map. The mesh can then be simplified, saving both processing time and memory while retaining much of the detail of the original. Having a surface that is smooth but has differing shading normals is not something we usually see in the real world. In reality, bumps are what cause the surface to change its orientation. However, it's fine in computer graphics to have one without the other. We've already been using the idea that the shading normal can be different than the geometric surface normal. Here we're extending that idea, varying the shading normal per texel instead of per vertex.